Okay, hello. So let's get started. First, I want to say sorry that Dr. Tan can't come because some reason. So today we two are going to make the presentation instead. I'm Lee from KollaHands-on, and this is my colleague Niao. So the topic here is training OpenStack for HPC. So we are going to talk a little bit about optimization and experiences gained from running HPC on OpenStack for TH-2 supercomputer. So here is the agenda. There are 4 sections included in today's session. First, I'm going to introduce some background and conventional HPC architecture about TH-2. Then I'm going to talk a little bit about the motivation to integrate HPC with OpenStack and the very high-level architecture designed for TH-2. After that, now we are digging into some more details about what we have done to meet the requirement to integrate a traditional HPC system and OpenStack to achieve the best performance in our system. So the last part is a short demo which will demonstrate the workflow from an end user's perspective. Some background. So what is TH-2? TH-2 is a supercomputer developed by China's National University of Defense Technology, the most powerful computer in the world, which can operate at nearly 34 petaflops per second. It's hosted at the National Supercomputer Center in Guangzhou, located in southern China. The specification. So the whole system contains about 16,000 computer nodes, each comprising 2 inter-Ivy bridge and 3 Xeon-5 core processors. And another thing I want to mention here is there are some other nodes include GPU inside, not mentioned here. So the interconnection is 48 gigabit per second, and it's called TH-2 Express 2, which is designed by UDT. So each node processes 88 gigabytes of memory total, 64 for Ivy bridge and 8 gigabytes for Xeon-5. And there are nearly 1,000 nodes running on the cloud in production now, based on OpenStack currently. The application running on TH-2, including big science, big engineering, industry upgrade, and information construction. So the system is built to provide both HPC service and information infrastructure. This is also one of the reasons to adopt OpenStack at our cloud platform. The software stack. As we can see in the picture, the whole software stack comprising include 3 layers. The bottom is system environment, including specially optimized OS, parallel file system, and resource management system based on Slurm. The middle part is the application development environment, many some enhanced libraries and compilers, which are also highly optimized for scientific and technical computing workload. The top part is comprised of HPC applications introduced in the previous slide. So HPC system which include many programming languages like MPI, OpenP, C-Fortran, and so on. So this is the very high-level architecture for conventional HPC. There are 4 types of node: computer node, I/O node, and login node. And there are 3 types of network total. The high-speed interconnection, which we called TH-2, used for workload. And there is another high-speed interconnection for the storage for Lustre. The other part, the left part, it Ethernet access for external user, and another one Ethernet for management. So there are a couple of issues for the traditional architecture. First, scalable. It's not easy for users to scale or shrink a cluster in the conventional HPC world. Second, customization. The traditional HPC software stack is usually stable and single. Let's say that if a user wants to use a different compiler, one has to first contact the sysadmin to install it on each node, and that may encounter some conflict issues. Then the sysadmin need to assign the node, a specific node manually for the user. So the whole process would take days, which is very ineffective. The third one is security and isolation. It's very hard to manage different zones for different requirements in the conventional HPC world. The last one is self-service. From a user's perspective, they may want to self-service for resizing and managing their own resource, and it will be more efficient than the traditional way. To solve all the problems mentioned above, we have to refer to cloud-based solution. So why OpenStack? You know, OpenStack is very flexible. Users can apply their resource on demand, and also it supports mixed architecture. Example, it supports managing node with or without accelerator together. The second one is multiple tenancy, which is very important for us to ensure resources isolation. The last one, but not least, anything OpenStack is open, as we know. So we can quickly solve problems with the help of the strong community. So let's go to the architecture after mixing HPC with OpenStack. So I don't want to go through too much details here, but there are a couple of components I'd like to highlight here in order to build a full functional HPC cloud. As we can see in the left corner, we use LXC Nest container for computer virtualization. And the storage path, we use Safe and Lustre both. And in the top of the picture, we use an open source orchestration tool, Elasticluster, for HPC cluster orchestration for end user. So now we are digging into more details in the following part.
Okay. Test. Okay. Hypervisor, for example, KVM-based visualization has been used as a fundamental technology in cloud computing. However, it has the inherent performance overhead in the virtualized environments, more especially the virtualized I/O device. To alleviate such overhead, PCI passthrough can utilize to have exclusive access to I/O device. However, this way prevents the I/O devices from sharing with multiple virtual machines. Single-root I/O virtualization technology has been introduced for high performance interconnects such as InfiniBand to address such sharing issues while having ideal performance. On the other hand, with the advance in container-based virtualization, for example, Docker, it's possible to reduce the virtualization overhead by deploying containers instead of virtual machines. The near-native performance can be obtained. Linux container is a user-space interface for the Linux kernel containment features. Through a powerful API and single tools, it lets Linux users easily create and manage system or application containers, allowing processes to be separated inside their own namespaces and file systems. Better performance than traditional hypervisor-based virtualization and share the kernel with host. Compared to Docker, Linux container is more conducive to running multiple processes, for example, SSH, Slurm, and it's easy to support large amount and integrate with itself. Some applications may not roll into default virtualization environments, such as high-performance Linpack. So we choose the Linux container as the virtualization layer. So what we do is allowing boot Linux container from sub-volume and implement the Lustre plugin. All OpenStack services running in container, including Lustre agent, because of deploying OpenStack with Kolla. To monitor Linux container, we should map C group in Docker and configure libert agent for agent. The picture shown is a CPU utilization pack of a Linux container. The storage we choose Lustre and Ceph. Lustre is used to store high-performance user application data, and the Ceph for glancing images storage and Nova instances images. After our research, there are 3 ways to use Lustre. First, mount Lustre in container directory. Second, send the driver for Lustre from DDN. And third, file system mapping from host to container. First, mount Lustre in container is straightforward and mount on demand, but data security can be problematic. The main drawback in implementing data to OpenStack clients is that file permissions are enforced on the client side. The data could be accessible by all tenants having root access to instance. The second solution, this achieve is more likely a cloud solution. It implements a larger Cinder driver by expose scalable Lustre namespace to multiple virtual machines on multiple spoke hosts. The link below is a patch. But unfortunately, the patch doesn't have any activities anymore since last year. The advantage of this solution gets more performance, and the larger Cinder driver provides block storage to OpenStack's computer service as well as other third-party Cinder driver. The main disadvantage, it can only provide volume storage, no file system sharing among containers. The third solution implements an isolated shared file system for each tenant. As we can see in architecture, you need to mount Lustre on each computer host first. The mapping is automatically to a container when booting from Nova. The advantage of this mount really means a lot for our HPC system. Almost no performance loss. HPC applications can run on the mapping shared file system as its own host. The user can only access directory which is exposed to them. The only disadvantage is that it's not so flexible. Subdirectory is cat-holded for each tenant. So it may only suitable for container. In order to boot the container fast and efficient, we implement an RBD-NBD driver for Nova. First, mapping kernel RBD on host, then passing the host device to container. This solution is straightforward. Implement is pushed to GitHub. If you are interested, refer to the link below. 3 types of networks in our system. TianHe-2 virtualized for virtual environment, 2 Ethernet for platform management and external users. If nearby network is used for Lustre internet connection only. The overview architecture for TianHe-2 virtualization support. First, large-scale layer 2 network support more than 8,000 nodes. Second, TCP and TCP/IP over TianHe-NI. Third, virtualized over raw networks for cloud platform. In order to achieve self-service Slurm cluster, we choose for orchestration tools, Elasticluster. Aims to provide a user-friendly command line to create, manage, and set up computing clusters hosted on cloud infrastructures. Install configuration file to define cluster templates. Can start and manage multiple independent clusters at the same time, and easy to scale up and scale down a running cluster. Support automate, set up all HPC clusters, even big data cluster, Hadoop, and other distributed storage clusters. In our case, we only use Slurm automation feature currently. How to set up Slurm with Elasticluster is pretty simple. First, install Elasticluster in virtual environment. Second, set up provider to OpenStack, the login part for image, and set up Slurm section like how many front nodes and computer nodes. Third, use a simple command line to create the Slurm cluster. On the other hand, we also have some optimization based on what most people do, like turn off a hyper-threading for CPU-intensive applications, running with no energy saving mode, use CPU pin and disable NUMA, and the PCI passthrough. This part for the Linux container may a bit different from the traditional virtualization. The next 2 slides would demonstrate that. The architecture here is a classical GPU pass-through case for KVM, and the picture on the right is for vGPU for some limited GPU models. GPU pass-through is more commonly used in HPC world. GPU pass-through relies on a number of technologies that you might be checked. If it's supported on your hardware, you will not be able to do this on your machine unless the following requirements are met. Your CPU must support hardware virtualization and IOMU. Your motherboard must also support IOMU. For this container, GPU pass-through could gain better performance than KVM. It's low cost and lightweighted. Using C group to control the device mapping access. The implement architecture shown in this mode makes sure how GPU driver installed on the host system and the right permission for device file. Edit the container config file to other entries for the NVIDIA devices. To make the NVIDIA devices appear in Linux container, install CUDA SDK without the driver, or use CUDA binaries directly in the Linux container. Couple of steps needed to make it work with Nova. Configure Nova, compute the PCI pass-through whitelist. Configure Nova and schedule. Set the frame related to Nova PCI alias. Finally, we can boot the Linux container with the pass-through GPU card with the flavor created above. We did some simple benchmarks with impact on TianHe-2 with 2 computer nodes. It shows there is 3% performance loss in container overall. The test we did is a bit simple. We will do some comprehensive tests in future. Now, let's go to the demo. Lee.
So we will have a quick little demo. Okay, as we can see, the screen, the right part is the command line help message for Elasticluster. It support, as we can see, it support a series of actions like step, stop, list, and recite, and something like that. More. Let's get started. Okay. Check if we have created before. Nope. Okay, just one simple command to create a Slurm cluster. So this may take about 1 or 2 minutes. As we can see in the left screen, three container it's already in build status. Okay, become active. It's pretty fast. And in order to configure the cluster, we need to attach floating IP for each container. Okay. There may be some setup in the container. Okay, let's just wait. All right. The configuration, it started. Okay, so as we can see in the right, it using Ansible to install and configure the cluster. Okay, this may take 1 or 2 minutes, so I just skip this part. To this. Stop here. As we can see here, we have a front-end node and 2 computer nodes. And there we can use this command to log into the front-end node. And after that, I will check if all 3 nodes are sharing the same directory. Yeah, there's a Hello World application. Log into the first computer. Okay. We have both. As info to check that if we have all these 2 computer nodes here. Okay. Run a concurrency task using SRun with 2 computer nodes and 10 concurrency threads. Okay, this is the demo. So, just all right. So, just a quick recap. In this session, we introduced how we run an HPC cluster at a service on TH-2 by combining HPC and OpenStack. with the help of some technologies like LXC device and file system mapping, and with the orchestration tool, Elasticluster, and maybe some other tricks to make the whole thing happen. So I have 15 minutes left. I'd like to show you live. Check if we can connect to the node. Can you see that? It's clear? Oh, it's connected. So I'm going to show if our hypervisor is using LXC. Oh, I need some help. All right. So in this demo, I have one computer node. As we can see here, the hypervisor type is LXC. And check. Yeah, this is the cluster I created last night. So this is all we want to sharing today. So any questions?
How many computing nodes controlled by OpenStack?
About 1,000. 1,000.
1,000.
Yeah, with 3 controller nodes.
Okay. And how many all of them?
Sorry.
How many computing nodes it has? TianHe-2.
Computer node?
Yeah.
1,000 computer node.
All of them is operated by.
Yeah. Operated by OpenStack. Yeah, we have 16,000 nodes totally, but only 1,000 operated by OpenStack. Okay.
Did you consider about using Ionic instead of hypervisor?
No, we didn't try that.
Okay.
Maybe in future we may try Ionic.
So, can you show the comparison graph? Go back to the. Can you go back to the performance comparison?
Which one?
The slide before demo slide.
Okay.
Yeah, this one. Do you know
Oh, sorry, there's an error here. We only have one computer node, so this one it's error. Yeah, sorry about that.
Thank you.
Any more questions?
How about XeonPi? XeonPi is used in virtual machine.
Sorry?
XeonPi.
XeonPi.
Interface.
XeonPi. Okay. We don't try to pass through that, so not included in today's session. Okay. We will try to pass through XeonPi to the container in future. Okay.
Is it possible?
Yeah, I think it's possible. Okay, thank you.